for me a great honor to introduce Jeff Scargle as the author of this talk today, because Jeff was for me astronaut by the writing reading his paper on astrostatistics, in particular the paper on which I learned the discrete Fourier transform and how to deal with this kind of data. And he has a long story within Ames and 41 years. He has now 70, 75. He is now working. You are not done. So for me it's an example of work. So his undergraduate study was in Poland, and he made his PhD in the University of Berkeley or Santa Cruz.
No, Caltech.
Caltech, okay. And well, his most famous paper is a paper cited more than 4,000. His paper were everyone cited to investigate periodicities in a time series. This is the most cited paper, but I asked him for the less or for the non-cited paper, or for the paper that you are not so happy, for the worst paper you never tried to write. And this was Fourier transforming the universe. That's true. So Fourier transforming the universe has been a paper that never would be the possibility to read because it's not published.
Actually, it will be published.
It will be published, because you tell me that.
I kept pushing.
Because the referee was not so kind. So, wow. Okay, so that's all I can say. Thank you for coming here to this meeting, to this workshop, and it's up to you to.
Thank you, but I don't need a microphone. Okay. Well, thank you very much, Ralph. I'm very honored to be here and to be invited. And I want to get right into the talk because it covers the entire universe, so we have to keep going and stay on schedule. What I'm going to try to do is to take you through a tour of the dynamic universe. And the point of view here is that when I first started in astronomy many years ago, as Rafa stressed, it's been a long time, the picture of the universe was that it was a very quiet, orderly place. The clockwork universe is a phrase sometimes used to refer to the planets moving in their orbits very smoothly and everything in its place and running like a clock. And during the last 100 years or so, we've discovered that that's not true at all. The universe is full of active things and explosions and dramatic events. Many of them discovered by space projects, NASA and the European Space Agency and so on. Almost every time a new wavelength regime was explored with rockets or satellites around the Earth, we discovered things are dramatically changing with time. And so that's the thread here, is that the universe is a dynamic, active place, not a clockwork at all. And at the end, I hope you will see that there are kind of two messages or two things that I'd like to get across. One is sort of, I don't know quite how to say it, but the arc of events in my career, starting with one thing and then going on to other things, and at the end well, maybe not the end, but as time goes on, what I started with is coming back into importance and in kind of an unexpected way. And then the other thing is just a pragmatic thing with data analysis, that scatter plots can be really interesting, and I hope you'll see at the end what I mean by that. So here's kind of the list of, this is kind of like a tour guide schedule. These are the elements of the universe we're going to investigate, and I'm not just going to read it. Let's go immediately to what people here probably have studied more than I have in terms, I see that there's some interest in solar astrophysics here. And it's almost common knowledge since maybe 20 or 30 years that the sun is not a quiet place itself. And here's a video showing a giant flare. I guess this is a prominence. Like I say, this is not kind of my field, but this is the active sun. Luckily, the sun isn't too active, because we would be in trouble here on the Earth if it was more active than it actually is, and that's kind of an interesting philosophical question. That are we here because the sun isn't active? And here's another. This is now a flare, and I think you'll see what goes on is there's an input of energy, a burst of energy appearing near the top of this field of view, and the influence of that energy spreads out. It's like a wave that propagates throughout a big region of the sun. It's almost like seeing a forest fire spreading out into burning up a bunch of trees. But of course we know a lot about the plasma physics and what's going on here. So in our very local neighborhood, we see a lot of activity. Here's one thing I have done with solar data that I think some people interested in planetary detection and exoplanets may be interested in. The top plot shows some measurements over many decades. The time, see, I guess I have a pointer here.
I think it's wise to put the charger.
Oh. Okay, well.
Just continue. Okay.
Yes, good, thank you. And the top plot shows from starting in 1980 to 2010 are measurements of a feature of the solar spectrum that indicates chromospheric activity. The chromosphere of the sun is a region kind of up above the photosphere where interesting activity is going on, but it's not as hot as the corona, which is a layer above it. And these data were not from images of the sun. They're what's called whole disk data, so that each point represents the strength of this, technically it's a calcium absorption line strength, but integrated over the entire disk. So one has no information about what different parts of the sun look like. And the reason I stress that is that's the kind of data we get from stars. The sun is close enough so we see it as a disk, and you can see nice pictures like I showed earlier. But with stars, we never have that. We just have all of the light from the stars in one point, more or less, and so any measurement refers to an average over the whole disk. So you would think you wouldn't get any information out of this kind of data about what's going on at different parts of the disk. And what you see, these rectangles that have and arrows show a kind of a blow up of the data for that period of time, and you see that there's a lot of detail. The up and down fluctuations are not noise or measurement error; they're true measurements. And what's going on there is that the up and down is at the period of the rotation of the sun. The sun rotates at a known frequency, and so that's what's happening there. And so by studying this data in using what's called a time-frequency distribution, it's like a power spectrum. It's a kind of a technical thing, but the basic idea is that it shows, if you draw a horizontal line, you see a spectrum of the variation at the frequency corresponding to the horizontal axis, and the vertical axis is time. And so there's some noise and so on in the background, but what you see in the middle region here is variations in the frequency of the rotation. And the point is that the sun has what's called differential rotation. The equator of the sun rotates at a faster speed than the poles, and so there would be a change in frequency with latitude on the sun, and that's what these vertical lines are at the equator of the sun at 30 degrees latitude and 60 degrees latitude. So these features that show the change over time correspond to motions of the chromospheric features in latitude. And if you're familiar with sunspot motions, there's a famous butterfly diagram that shows this effect, and it's called differential rotation. And that is the effect I just mentioned, that the rotation speed is different at different latitudes. So it's a little technical, but the point is, using this technique, you can extract information about what's going on the disk of a star, even from data that has no resolution on the disk, that doesn't give you any information. And so this technique can be used to study differential rotation in other stars. So let's move on out through the solar system. This is, you may recognize the planet Jupiter. Jupiter, amazingly, has a phenomenon on it, much like the aurora on the Earth, that is near the North Pole. Here's a blow-up of the North Polar region. There's glowing gas, very much like the aurora on the Earth, and it's changing over time. Here's a movie showing this activity. And I think very few planetary scientists expected this to happen, but when NASA's missions went by, we saw this kind of activity. There we go. I was going to talk a little bit, this is just a kind of a token slide about exoplanets, or planets around other stars. NASA has done a lot with that, and the Kepler mission is at NASA Ames, where I work, but I know a lot of people here are interested in and have worked on this data and probably know more about it than I do. So I didn't want to go into a lot of detail, but I think this is one of NASA's most popular discoveries over the years, namely that almost every star in the sky has planets around it, and some of those planets are much like the Earth, and so there may be life on those planets. And so that's the key question: is there life on other planets elsewhere in our galaxy or in the universe? And even more, is there intelligent life? You may be familiar with the concept of SETI, the search for extraterrestrial intelligence. And here's a kind of a peculiar approach to the idea of maybe we can get messages from extraterrestrial civilizations. These are just cartoons, of course, but the idea, it's called star tickling, and the notion is that the civilization might not be able to generate enough energy to send powerful radio signals that we could actually detect at very far distances away, but they might be able to make use of a nearby star to send the information in kind of an indirect way. So the idea is that the civilization might send some kind of beam of energy. The Star Trek laser beams are meant to symbolize that. Might send some kind of a beam of energy into the center of a variable star, and to change its period by a little bit, to to cause enough of a physical change inside the interior of the star to make the period change a little bit, and so the star could be used as a telegraph signal, sending bits of information and thereby encoding a message. Well, that's a possibility. It's kind of far-fetched. It's hard to imagine how that would work, how you could get enough energy into the core of a variable star. But the variable stars, the reason why they vary is because they're unstable. They have instabilities in their interior, so a little kick may give rise to a big effect. So that's the idea, that you might be able to make use of the instabilities inherent in Cepheid variables, for example, or other variable stars. So to try to see whether this is happening, one needs to collect together a lot of data on variable stars and to see if we can actually measure a non-natural signal. The point is we have to be able to identify that it's a intelligent signal and not just a variation that is happening naturally because of astrophysics. Well, it turns out the best data for this is Kepler data. Kepler light curves, as you may know, are very accurate, and the Kepler mission, in addition to finding planets around stars, has collected together a lot of data on variable stars, and there's quite a bit of interest in the Institute here and that kind of data. And so this led to my trying to go through the Kepler archive and identify the variable stars that might be useful for this project. And this plot is a little technical, but the two axes are essentially the horizontal axis is an unusual way of measuring the period of the stars. You can think of it as like a frequency in a Fourier analysis, but it's a different approach to finding the same thing. So if the star is periodic, its period would be, the frequency is essentially the horizontal axis, and the vertical axis is a measure of how stable that period is. In order to be able to identify an intelligent signal, the star would have to be pretty stable. It can't vary all over the place because that would confuse the message. And so you need stars that are at the bottom of this plot and at the right-hand end, that is, have high enough frequency so you get enough information to get a real signal through. And so this is the first of three scatter plots I'm going to show. A scatter plot is just where you have two variables and you plot points for a bunch of different objects that have those two variables measured. This is kind of a mixture of points and a contour plot because there's so many points in here, the points would fall on top of each other. But the idea is that these stars down here are likely candidates for these messages that might be sent from an extraterrestrial civilization. So I'm obviously not going to announce that we found a signal, or you would have heard about that already, but the next step in the research is the hard one, namely how do you identify and make sure that a modulation that you see is really an intelligent signal and not just an astrophysical variability. But anyway, the first star I looked at was one at the right-hand end here, and that's kind of the plot. And this is a Delta Scuti. It turned out it's a Delta Scuti star, and I know people here are interested in these stars. So, nice idea, but in order to really identify what's going on, you need some kind of a way of deciding what is an intelligent signal as opposed to a natural variation or noise signal. So that's the hard part. So maybe someone in the audience can help with that. It's the same kind of problem that internet data scientists have to deal with in a way. So, here's another way, of course, to get signals from, or to try to see if there are civilizations sending a signal is with a radio telescope. And there's a number of different radio telescopes being used today to listen, so to speak, for signals like this. One of them is in California, the Allen Telescope Array, that for about 10 years has been collecting signals that are unusual, and they've recorded the time series from these radio signals, but it's really hard to know whether what we're seeing here is an intelligent signal or not. These are little postage stamp images that are like the plot I showed for the solar data. They're time frequency. Time is running in the vertical direction, frequency in the horizontal direction. And what you see are lines that correspond to a Doppler shift in the signal, because maybe it's a spacecraft exploring the solar system, so it's drifting in frequency. But all of these signals are almost certainly noise signals, what's called radio frequency interference. Unfortunately, even in this kind of remote area of California where the Allen Telescope Array is, there's still a lot of radio frequency interference from even just a car being driven by with a faulty ignition can give rise to interference signals that are generating this kind of thing. So there's a huge database of over 100 million of these signals that have been recorded over 10 years. And it's like trying to find a needle in a haystack. You have this huge stack of hay, and you're looking for a needle, and it's even harder because you don't know what the needle looks like, and you don't know what the hay looks like either, because we really don't know a lot about the nature of these interference signals. But again, a scatter plot comes to the rescue. Here's a scatter plot based on just plotting two simple parameters for each of the signals. If you take each one of these time frequency distributions and plot what's called the standard deviation, the degree of variation in the horizontal axis against the standard deviation in the vertical axis, it's just kind of the simplest thing you could think to plot for these time frequency distributions. And here's what you get when you make that scatter plot. When I first did this, I thought it would be just a big blob of scatter, and you wouldn't be able to make much sense out of it. But almost by magic, there's a classification that falls right out of this scatter plot. And you can identify this intricate filamentary structure corresponds to different classes of radio frequency interference. Some of them are what's called broadband, that is over a wide range of the frequency spectrum. Others are narrow band, but on and off in time in various ways. So this simple idea of making a scatter plot of these data led to a nice classification scheme. But again, that's only sort of preliminary to the final problem of can you identify intelligent signals here? But at least it gives you a way to rule out a whole bunch of these interference signals and throw them away and not worry about them. Okay, now we're going to leave the area of the solar system and the area of stars near the Earth to a fairly distant object. This is the first known image of something called the Crab Nebula. This was a drawing by the Earl of Rosse in 1850. If you know the history of astronomy, he had a pretty large telescope and drew this image of a nebula, a cloud of light on the sky, which in those days they didn't understand what they were at all. And it kind of looks, I don't know if that looks like a crab or a lobster or what, but it's been given the name of the Crab Nebula. Here's a modern photograph, this was kind of the beginning of my research and my PhD back decades ago at Caltech. This is an image of the Crab Nebula taken through the 200-inch Palomar telescope, and you see. To make a long story short, the light that you're seeing is from high energy electrons. This nebula is the remnant of a supernova. Excuse me, a supernova. That is a star that exploded in the year 1054, and 1,000 years later or so, we see an expanding blob of gas that's left over from the star that exploded and ejected this gas. And this gas is glowing because of what's called synchrotron radiation, that is high energy relativistic particles moving in a magnetic field. And my studies concentrated on features near the center of the nebula that were moving around. In a picture taken a few weeks later, these features would be in a different position. And I actually have some slides in the wrong order. And here's, this is a crude graph. Some of you may remember back in the day when you made graphs with ink pen and paper instead of on computers. So this is actually from a publication that today the editors wouldn't allow something this crude. But anyway, what's plotted here are the positions, the measurements of the locations of some of the features that I pointed out on the image of the Crab Nebula. And for example, that shows a very fast motion out away from the center of the nebula, and then it turns around and comes back. And if you calculate how fast these objects are moving, because we know the distance to the crab, we can calculate the true motion, and these motions are at a big fraction of the speed of light, like a third of the speed of light. And at the time, that was kind of spectacular, because of course nothing can move faster than the speed of light. So these are just relativistic motions that are really hard to understand what's going on. And then this is, now we know what's going on. This is 30 or 40 years later, X-ray, this is an X-ray telescope image of what's going on at the center of this nebula. This is a movie that keeps cycling through, but what you see is the features that I plotted on that thing, on the previous graph, showing motion outward, corresponds to these outward moving waves. And so now we know that there's relativistic waves being generated by sort of unknown effects going on near the center of this nebula. We now know, with something I didn't know at the time I did that work, is that there's a pulsar, a rotating neutron star at the center of this object, and that's almost certainly what's generating the energy. Okay, so let's leave the Crab Nebula and now go to the center of our galaxy. This is even farther away by not a big factor, but the center of our galaxy is a bit farther from the Earth than the Crab Nebula. This is what the center of the galaxy looks like from the Earth, looking out from a mountaintop. And here's one of the most, to me, this is one of the most spectacular results of modern astronomy. I had little to do with this myself, but this, to me, was the final proof that that black holes exist. There was a lot of ideas that black holes should exist based on physics, black holes being super dense concentrations of matter that are so dense as to be almost infinitely dense, and no radiation can get out. And I assume you all kind of know the basic idea, but these were just theoretical notions that black holes could exist, and there were some sources that seem to indicate they might be black holes, but what we found was that at the center of our galaxy there's a well, I can't say a star because there's nothing there. There's a point where there is presumed to be a black hole, and what I'm going to show is a movie that shows the stars near that object orbiting it under the gravitational field. So what you see over the period of time, at the top is the date, so you can see the years go by. So these stars are all orbiting this point, and there's nothing, we can see nothing there, and you can figure out how much mass there must be based on the following the orbits of these stars and knowing the gravitational fields and so on. And it turns out there's got to be a big mass there, but we can't see it. So that's kind of proof that it's a black hole. And I think after this result from the UCLA group, no one could still be skeptical that black holes exist. And in fact, now we know that almost every galaxy in the sky has a black hole at the center, and our galaxy is no exception. And not only is there an object there, but it's not completely black. There's some faint X-ray radiation coming from the object. You can't see it too well in the dimness here, but there's a flashing on and off or irregular variation because the material that's falling into the black hole and the gravitational field is so strong that the matter is heated up and emits radiation, in this case X-rays. And here's another X-ray variability. Again, the theme here is variable light coming from objects. Here's a binary system. It's called SCOAX-1 that some of you may know about. And this is some old data from a satellite called EXOSAT, which was a European Space Agency mission that some of you may have been involved in, I'm not sure. And this is, again, the horizontal axis is time, the vertical axis is the X-ray, the brightness of the object in X-rays. And we got a hold of this data from the project, and it's a perfect example of what's called a fractal light curve. If you take this light curve and look at its behavior, it looks random but with some structure. And if you blow it up by expanding the time scale, the structure looks the same. It's what's called scale invariance, that there's no fixed scale. There's no periodic variation here. It's random and has this peculiar fractal-like property that means you can't really distinguish one time scale from another. And so we did an analysis using what are called wavelets to look at the amount of variation as a function of period with using wavelets. This is very similar to what you could do with Fourier analysis and power spectrum analysis. The horizontal axis is time scale in a logarithmic scale in powers of 2 instead of powers of 10. Wavelets are kind of tuned to powers of 2 instead of powers of 10. And the vertical axis is the amount of power. And I won't go into a lot of detail, but basically what is seen here is roughly a linear dependence of power on scale, but with a feature in it. This bump is what's called a quasi-periodic oscillation. That is, it's not a rigidly defined period, but at roughly the time scale corresponding to, this would be 2 to the 6th power times the basic unit of time is 4 milliseconds. So whatever that number is the frequency, but it's not a sharp feature. It's called quasi-periodic, meaning it's a broad feature in this spectral decomposition. And so the solid line is the data, and then the dotted lines kind of surrounding it are theoretical models based on kind of a crazy idea for what's causing the variability, something that is called a dripping handrail. And the workshop that we've been having here over the last few days has been devoted to similar models and dynamical systems. And I don't have time to go into details, but it's a very simple picture of what's generating this this behavior, this variability that changes with time scale or frequency in this kind of peculiar way, and the model fits the data very well. And at the time, and I think it's still true that this is kind of a breakthrough in a sense that before this model came about, this QPO was known. This isn't we didn't discover this feature, it was known, but most of the ideas, the theoretical ideas from what it was, were that it was some feature connected with orbital motion. This is a black hole, this is a binary, it's not a black hole, it's a neutron star binary that's somehow connected with that orbital system, and that the basic, it's called 1 over F noise, or roughly linear dependence of variability on time scale, was a completely different phenomenon. What this showed was that the entire spectrum, the 1 over F noise and the QPO superimposed on it, come from one simple physical mechanism and not two different ones. So with the idea of simple is better, this was a kind of a better picture. So this is a kind of a little technical, but this model, it's a very simple physical model, but there are three different mathematical representations of it. The top one is representing the physics in terms of differential equations, and then solving the differential equations in the usual way that astrophysicists do. But there's a way of representing the physics in a more discrete way. Instead of having a continuous picture as in differential equations, there's something called a map lattice, which represents the same physics but in terms of finite differences instead of differentials. And then there's an even more discrete representation where all the physical variables, time and space and the brightness, are represented in discrete ways, and this is called a cellular automaton. And these three different mathematical solutions for the behavior of this physical model in kind of a peculiar way all look kind of similar, and the basic underlying physics is the same. You don't need to know the details, but this is almost like a time frequency plot. Frequency is the vertical axis in each case, so it's given slice is the power spectrum. The horizontal axis in this case is the physical parameter, representing the amount of accretion, the rate at which matter is falling into the center of this postulated system. And what's intriguing is that with different values of this relative amount of accretion and diffusion along the dripping handrail, you can have periodic solutions. The spectrum down here would be three different periods, the fundamental and two harmonics, but at other values of the parameter, there is no period. It's a random process. So this is a case where the model with just slightly different parameters can give you periodic behavior and random behavior. And here's another, this is now we've left our galaxy, and this is Kepler data for another galaxy outside of ours, which again has this kind of fractal-like light curve. You can almost see it with your eye, that the gross random behavior is kind of mimicked in the detailed behavior. And if you take this kind of data and plot it on different time scales, it's hard to see any difference. It looks the same statistically on different time scales. And now we're going even farther away to gamma ray bursts. I don't know how many of you were here for a talk in this series by Jerry Fishman on gamma ray bursts, but I think he talked about. These are the most spectacular exploding events that we know of in the universe. This is not data. This is an artist's conception of what's going on. That there's some kind of collapsing system with jets and so on. But this is basically pretty fanciful because we don't really know the details of what's going on in gamma ray bursts. But here's some data from some gamma ray bursts, and I guess I'm going to kind of skip ahead, skipping over some details, but the point of this is to show that when you analyze the data, you have individual times of arrival of gamma ray photons, and so to make a light curve out of it, you have to bin those times, and what the light curve looks like depends on the choice of how big the bins are. So if you have big bins, it looks like there's just one pulse, but if you have finer bins, it looks like there's several pulses, different features, and so that's an ambiguity. How do you decide what's real and what's just random variation? Well, there's an algorithm that we developed at Ames and at the group at San Jose State that solves that problem by essentially binning these arrival times in a way that where the bins are not predefined. You don't decide ahead of time where the bins are and how big they are. The bins are defined by the data, and that's what these. I guess we just concentrate on the blue lines. Those are bins of the raw data defined by the algorithm, and so it tells you what is real in this data. That over this interval, those fluctuations are just statistical random noise, but the change from here to here and from here to here and so on is real variation. And here's another. Now we're kind of getting even more exotic and modern. This is a recent discovery that I'm sure you've heard about, of two black holes that collided and generated gravitational radiation, and that's a big deal because it's the first time in a billion years that we've gotten information from in the universe in other than light, other than radiation. It's not quite true because cosmic rays are particles, but anyway, this is a new way of getting information about what's going on in the distant universe. And this is a theoretical, if I can get it going, a theoretical calculation of, well, I guess that's not going to work. Anyway, the movie shows an animation of a theoretical calculation following the orbital motion of the two black holes about each other. But what was observed was a pulse of gravitational radiation at two different sites on the Earth. One they're both in the United States, one in Hanford, the state of Washington, and Livingston, Louisiana. And in each case, it was a clear signal superimposed on the data as a theoretical model of what the signal should be like, the so-called numerical relativity, numerical calculations of this collapsing binary star system. And in both cases, the signal was clear and agreed with the theory, and there was a time lag that allowed between between the two different observatories that allowed us to calculate roughly the direction to this source. And this is going to just the importance of this whole new field of astronomy is going to grow over time. And okay, now here's at the beginning I said something that I did a long time ago is kind of coming back into relevance. Here is measurements of gamma ray radiation from the Crab Nebula from the Fermi Gamma Ray Telescope at Stanford, and it's an international collaboration with NASA and ESA is involved too. And it's completely unexpected in the sense that the Crab Nebula was known as a gamma ray source for many years, but it was thought to be constant over time, that there was no variation in it at all. But that turned out to be not true. There's this definite increase in the brightness at these intervals of time over just a short period of time. In the sharpest rise, the flux doubled in 8 hours. So it's a very rapid change in flux. It's almost impossible to understand. And the basic puzzle is that we know that this flare is not coming from the pulsar or anything connected with this activity near the center that I was talking about, that whatever it is coming from out in the nebula, that in the region where those features that I was talking about earlier are moving around. So it probably has something to do with relativistic plasma motions in the outer parts of the nebula, but the mechanism is not known at all. So here's a detailed analysis that I did using that algorithm that I showed earlier, where you essentially bin the data in a way that captures the changes in brightness. The top plot shows the flux of gamma rays over 800 days. That's at that point it was how long the observatory had been in space. And then the red line is this so-called Bayesian block analysis, where the algorithm tells you nothing is changing here, but there's a statistically significant change here, 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 and here. And in fact, if you blow this region up, what's down here, you see that this feature is really 3 different spikes that are separated and cleanly separated in time. And so this algorithm is kind of developed to apply to this kind of data, and it's very informative about the detailed time dependence of what's going on here. Let me skip this. This is a theoretical calculation that has to do that's interesting in that it's a way of measuring, of possibly detecting the fact that relativity theory isn't quite right and that the speed of light isn't exactly constant. But this hasn't really been completely verified by experimental data, although the Fermi Gamma Ray Telescope gives some indication of possible. See, the idea here is that if there's a tiny difference in the speed of light for low energy and high energy gamma rays, these gamma ray bursts are so far away that little difference in the speed of light would accumulate over billions of years, and there would be a measurable delay in a sharp feature in time if there was this possible variation of the speed of light. And so it's one way to check relativity theory that's still work in progress. And here's this is now kind of going in a different direction. This is showing that some of the algorithms that extract time information can be used to extract spatial information. This is a we now have lots of data on the positions of galaxies in the universe, where we know not just the position on the sky, but the distance to each galaxy. So we can get a three-dimensional picture of how galaxies are distributed, and they're not random, they're just distributed in these features in clusters and in what are called filaments, that is linear structures. And this is another ongoing area of research. And let me conclude with these last two things are kind of just spin-off things that aren't really time evolution or dynamics as such, but they're data analysis problems where the same kinds of algorithms can be used. This is some genetic sequence data. I'm just learning about the biological significance of these things, but this is part of the human genome where what is plotted horizontally is the position along the sequence, 0 to 10, which is really a factor of 10 to the fifth, because this is a segment of the data that's a million base pairs in the DNA sequence. Anyway, this is chromosome 19, and it's much longer than this. It's just a part of chromosome 19. And the vertical axis is what's called the GC fraction. You may know there are 4 symbols in the genetic code, and G and C go together, and the fraction of G's or C's in the sequence has some important significance. And this Bayesian block analysis has been used to identify intervals over which the GC fraction is either larger than average or smaller than average. And it's hard to make sense out of this, but once again, this is the last of the 3 scatter plots. Here's a scatter plot showing the 2 parameters. One is the length of those block intervals that the algorithm comes up with. In the logarithmic scale, this is 100 base pairs, 1,000, 10 to the fourth, and so on. And the vertical axis is the GC fraction. So what I'm trying to show here is if you get data that's complicated and messy, if you make a scatter plot, you may find some interesting structure. This now shows the data for the entire human chromosome 19. And again, before doing it, the thought was it would be just a random mess, but you see there's interesting structure. And in particular, there's vertical clusters at multiples of kind of a magic number, which I had no idea what the significance would be, but this is 144 base pairs, and that's twice that. And it turns out that's kind of a magic number in the biology of the genetic, the so-called double helix. And I think, yep, that's it. So we've now sort of toured not only the entire physical universe, but we've gone off at the end into some other areas, biology and the structure of the universe. So again, it's been a pleasure, and I hope you enjoyed this kind of random tour of the universe. Thank you very much.
Any question? Ricky?
Thank you for your nice work for this numerical technique. With respect to the possible difference in speed of light,
Yes.
different energies,
Yes.
you mentioned yesterday that it is difficult to ascertain because maybe you don't really know what the origin of different energy bands is.
Yes.
But I'm just thinking whether you could use 2 line transitions which come from the same upper level, so that the excitation rate is fixed by atomic physics, and but they do come to a very different low levels. They have very different energies. Whether that would be good parameter to track these different speed of light.
Yes, that's an interesting idea. Unfortunately, gamma rays are not line radiation.
You wouldn't see that in X-rays.
Right, but gamma ray bursts don't emit X-ray. Well, oversimplifying it, but basically, you're in this particular approach, you're limited to gamma rays, and those are not lines. But some X-ray lines have been detected, and that's an interesting point. I'll have to think about that. I have a feeling Mother Nature could figure out a way to thwart that idea. And could you be really sure that the two different wavelengths were emitted at the same time? But very interesting idea. You know.
And I'm a little embarrassed to ask this question, but you show us here a variety of different intelligent algorithms to analyze data which is not regular.
Yeah.
So what is the need of the Fourier transform? Why do we keep using the Fourier transform? I know it's very powerful and very, but what's the need of it? Because it has a strong underlying assumption.
Maybe I should ask Rafa to answer that. He's the Fourier transform is I guess it's just a fundamental thing. It's the simplest way to represent periodic, to decompose any signal into periodic components. As Fourier showed, I don't know, hundreds of years ago, there's a unique representation of any time series, any variability data, as the sum of frequencies. And if that's what you're interested in, the kind of theme of what I've been trying to show here is that if you're not interested in periodicities as such, but more random variation, then other techniques are needed. And wavelets are very much like Fourier analysis, but they're kind of tuned to this 1/f noise and random variation. So I hope that answers your question.
Thank you for the talk. I have one question concerning the light curve of the, I think it was a gamma ray burst, in which you apply an iterative method to get rid or to discard what could be spurious, so not really signal, and then you left what might be interesting. I saw there was a peak that I would have interpreted as real, and this procedure removed it.
Yes.
So is there a double check? Is there a way, maybe like analyzing different parts or so, making the whole light curve into different pieces and checking if the same result was obtained? And I am asking this because I would have double checked why this peak
Yes.
was removed.
Yes. I guess I should have known people would look more carefully than I wanted at some of the details. You're exactly right. No analysis method of this kind is perfect, and there's always a trade-off between showing what's real and missing things. In other words, what are called false positives and false negatives in detecting structure. So in any method, there's like I say, a trade-off, and there's a parameter you can adjust that kind of mediates that trade-off. But the goal of the algorithm is that what it shows. I like to use the phrase from courtroom scenes: the whole truth, nothing but the truth. That is, it doesn't show you any noise fluctuations as being real, but you've made a good point. Certain details are on the margin of correctness, and they could be one way or another. They could be true or false, so to speak. So, and that's just built into the nature of statistics.
Thank you.
not for the talk, but for your whole career. I think that people who does this multidisciplinary work is the one who really put the seeds in different places and get the flowers in different places. And I want to be so poetic, so I wanted to go to the plot, the dispersion plot you made for identifying different kind of sources for radio signals, either instrumental or
set.
to show it up. Well, the nightmare of radio astronomers nowadays is how to remove interferences in this in this world full of sources for that. So I was wondering first if this plot you showed is published,
No.
or is that produced with a SETI collaboration?
No, it's kind of a long story, but it hasn't been published, and it may be, but it depends on things. But unfortunately, I'm surprised, but very little is known about radio frequency. You probably know this. That I was hoping that some of the SETI Institute people would be able to tell us what was going on, that kind of radio frequency interference is due to atmospheric effects or a local television station or what. But there's very little hard knowledge of what these radio frequency interference structures are. So I think that's limiting. The classification scheme that fell out, I think, is real, but there's no ground truth. There's no way to verify that it's really doing the right thing.
Because I think I wonder if this is known beyond this collaboration, this SETI collaboration, because it should be.
Yes.
It would be probably very useful to classify for SKA, I'm thinking, as you probably get. So I wonder if this is not published, maybe we as radio astronomers should find a way to transfer this information to the relevant people in these other projects.
Yeah, that's a good. Thanks for bringing that up, and I'll think about it. It was the result of a complicated collaboration with IBM Research and the SETI Institute and NASA, and there were some politics involved that were strange. So it's not a simple story, but I'm glad you think it might.
Shouldn't be lost.
Yeah, I'm glad you think it might be useful, and I'll pursue that. Thank you.
Thank you. Nice talk. The question will be too ambitious and too hard in the sense that is there anything we are learning about photon matter interactions in general after all these analyses? I mean, which is beyond the standard model of particle physics?
Oh, that's a good question.
For
Not
everything,
very much.
very much.
There are some notions of coherence. One could ask, are gamma ray photons that arrive from the other side of the universe, do they arrive in coherent bunch of boson condensates? And unfortunately, most of the gamma ray telescopes only detect the total energy, and the Fermi gamma ray telescope might be able to see in the tracks. If you're familiar with particle physics, it's a tracking system, and so thought about that a little bit, but there's no hard. There's a lot of interest in that. There's something called photonic astronomy. That, if you Google, you'll find a bunch of stuff, mostly in the optical range. But high energy astrophysics is really interesting. Just the fact that you measure details of individual photons, so you can get at information like you're speculating about, but so far it hasn't yielded any new discoveries.
Yeah, because my question is related to LSST.
Oh.
Because they will map the sky every 3 days, right? Also the whole sky.
Yeah.
And you will have all sort of transient
Right.
objects. So, but
Yes.
in practice, is there any hope to find anything which is exciting in that sense, but beyond the particular interest of a phenomenon?
I think not for LSST, because it is a more conventional CCD that doesn't detect individual photons, it detects many at once. But What do you think about that?
Well, but sorry, let me talking about the need to Fourier transform. Apart from being an essential theorem for the physics, I mean the Parseval theorem equating time and frequency, I mean this is another way to describe the real world. If you use the time, it's equivalent to describe the frequency. We are not so familiar with the frequency description, but it's also it's the same. But the question for us is critical because we are trying to describe an interior, a stellar interior in which the only solution are periodic solution. So this particular framework is crucial to identify peaks by peaks in the Scargle periodogram with frequency with eigenvalues, I mean the solution of a differential equation put to be solved in every shell of the star. So it's essential for us to take the platform and to identify the peaks with this say frequency of a given system. The question now I pose to Jeff is why there is always a residual which is not fit by the harmonic series. I mean, you have seen that any particular light curve cannot be fitted by an harmonic series. What's your opinion about this particular?
Well, that's a very general question, but the answer must depend on the kind of source and so on. But in general, I think it's a simple picture that variability can be composed of a small number of periodicities. I think the context you're talking about is there a fairly large number of periodicities, so it's a different context, but underlying any data, there's a mixture of sources. There may be periodicity superimposed on random variations, for example. In the SCO-X1 data, there was a quasi-periodicity plus a more random component, which we decided was really one physical phenomenon. But in other cases, there could be several physical phenomena mixed together. And you model one, and the residuals then include the other physical phenomenon. And so just in general, you need a more flexible model that allows for other things. We've talked about there may be non-random errors, there may be systematic errors. In timing data, there can be effects in the detector, dead time effects in the detector, and leakage in CCDs and things that complicate the error analysis, the instrumental uncertainties. But I'm really not answering your question in any specific way, but I think it shouldn't be too surprising that when you do what you think is your best job of capturing the physics with in the data, that what's left over still has more to tell you.
Okay. The second question related with arrow of time. What's the concept of arrow of time? What you can measure the arrow of time?
Yes, I didn't go into any detail, but the flaring in the Crab Nebula, I had on the slide, can you see the arrow of time here? It's a simple point, and that is take a movie of something and look at it, and then take the same movie and run it backwards. Do you see the same features? Does it look the same? Well, of course, in real life, for obvious reasons, it's very different. And you've seen funny movies where people are flying backwards. But in light curves, you have the same issue. If you have a light curve, and let's say you just plot it because you want to see what it looks like with time reversed, could you detect the difference? And for the SCOX-1 data, I'm sure you couldn't tell the difference. But the Crab flaring, there was a slight indication of rapid rises followed by gradual decays. If you reverse that, it's very different. It's a gradual rise and a sharp decay. The gamma ray bursts it's even clearer there. I didn't show that in detail, but it's even more extreme. And so the arrow of time is an important physical quantity. And as we've talked in the workshop, some of the conventional methods for deciding what's going on and modeling these pulses is insensitive to that and can't distinguish forward from backward time. So that's one of the research areas that I've been interested in. And that's related to the more philosophical cosmic arrow of time that you may be more familiar with in thermodynamics. That is, the laws of physics are time reversal invariant. Why is it that the universe isn't? That's a question that I defer to wiser people.
Well, thank you. Thank you for this.
Thank you.
For coming here. Very grateful to you for your work.
Thank you.